Good afternoon, everybody. Today we'll have uh, like different topic per unit system, and we are going to study per unit system in power system. But this one was included in the chapter of transformer in the end of the chapter of transformer. So that's a good chance. I mean, you have it if you're going to study power system because that's very important technique when you analyze any circuit or any system, single phase or three phase. So it's called per unit system. What does it mean per unit system? Per unit system is like you want to find quantities referred to a reference. And like, let's say that a person has $100, somebody has $200. We got to make reference so we can compare between the two people. All right. When you hear from one person, you cannot compare. Let's say I'm going to compare it to 100. So the 100 has one per unit. The 200 will be 2 per unit. If somebody has $50, will be 0.5 per unit. So it's close to the percent, but we don't multiply by 100. That's all. That's a per unit system. So per unit system, and it makes sense because when you hear any quantity, it doesn't make sense except you refer it to something. If I tell you the transformer has 10 amp or 50 amp or 1 amp, you cannot tell it's high current or low current. You got to refer it to something. So the per unit value, any per unit value, we'll call it the FPU, means per unit, and F could be current, voltage, power, apparent power, impedance, any electric quantity, will be equal to the actual value divided by the base value. And the base means the reference we're going to choose. Usually in power system or any electric system, when you choose, it's very important to choose the very basic references, the voltage and the power or the apparent power. The voltage and the apparent power. We call it V base and P base or S base. You can, I mean, I'd like to refer to S because I use the volt amp as a base. And using these two bases, you can drive the other bases. Like you want to find the current base, so you can express the current in per unit values. Very simple. We're going now to derive the other base quantity, but it's important to know you choose for any system two basic quantities as base, one for the voltage and one for the apparent power. Are we free to choose any quantity? Yes. You have a system, you can choose any quantity in the system as the base, or you can choose another value, any value not in the system. But usually, the engineering, they always use the rated value. They prefer to use the rated value. So if you have a motor, generator, and on the plate on this machine, there is the value, nominal values, the rate value, they use it as base. So they can compare it to something related to the device itself. So let's say that you choose the power base. When I say power base means I mean the apparent power base, volt amp base, and the voltage. How can you find the current base? Very simple. You divide the S base by V base. So if you have a system, let's say that you have a generator or a machine, and this machine you'll find that was written like it's 120 voltage. That's the rated value, VR. And the power of this one, let's say it was like 500, or choose again just power. Let's say that it was 480 volt amp. So that's the rated power. That's all what you need. You'll find other things. That's what you need. You make these two values. And then using these two values, you can say, okay, I'm going to choose the base, you call it B. The rated value. Do we have to? No, we don't have to. I can choose 100, 200, whatever. But once you choose it, it's fixed. So we prefer to choose the rated value, would be 20, and the power base will be 480 volt amp. So now I want to calculate the current in per unit. So you got to find the base for the current. Well, I base will be equal to, you just divided the power base by the voltage, you get the current base. So I'm going to divide 480 by 120, and I get 4 amp. It means 4 amp is the reference. So if you have 2 amp, it will be 0.5 per unit. Well, how to find the base for the impedance? You just square the voltage divided by the power of the base. And of course, there's a reason why you are doing that, because the Z is equal V over I, right? If you multiply, or I mean, if you say, what is current? How you got the current? Because voltage base, that's the base. And current is not the base. You try to get it back to the essential bases we use, which are voltage and power. So current, we just got it here, current by dividing S by V. So it will be V squared over S. That's how we got it. So the base of the impedance is equal the voltage square base divided by the power base. So that's, I mean, the quantity that you need. You need voltage, power. Okay, somebody might ask, how do we have to find the base for active power and reactive power? No, we don't, because all belong to the power category. So that's, I mean, how we can. For transformer, that's, I mean, we'll have slight change. Because in transformer, you got two sides. So if you have a transformer, usually in one line diagram, that's that transformer. And the base for the power is the same, because as you know, the power and the power is the same. When you look at the transformer, it's 120 volt by 1200 volt. So give you voltage on both sides, but the power is only one quantity. So S base is one quantity for transformer. But since you have Turner's ratio, you will have voltage base for the primary side, and you have a different value for the voltage base on the secondary side, because there are Turner's ratio, right? So that's, I mean, the only difference transformer. Just you got to choose two values for the voltage as basis. Accordingly, you will have IB1, you will have IB2, you will have ZB1, you will have ZB2. So you'll have reference for each side. Reference for each side. Okay, just let's take a numerical example. That's the example we're going to solve. Just let's stick to the words. All right. Can you see the example? Right. It's given the exciting current of a single phase 10 kVA, the information for transformer. So like, I mean, just to make simple, one line diagram, we have a transformer. That's what we're going to do. And it's 10 kVA. If it was not mentioned in the problem, the value of the basis, you are free to choose. So you prefer to choose the rated value. So I'll say the base for the power, it's the rated value, 10 kVA. All right. And 220, that's the rated value here, that 200 2200, and that's 220 voltage. So that's the rated value for the primary, and that's the rated value for the secondary. So now I'm going to say, okay, V base 1, that's, I mean, I always call this one, this 2. I don't like to give letters here. So VB1 will be equal 2200 voltage, and the base for the voltage on the secondary will be equal to 220 volts. All right. So now that's, we have 6 hertz. Okay, we don't care about the frequency here. The information was giving you exciting current is 0.25 amp and measured on the high voltage side. High voltage side means in 1. So I will call the excitation current I, we call it phi, right? I phi, and I write 1 because it's in the high voltage side, which is 1. It's given 0.25 amp. Okay. Now let's continue. Its equivalent impedance is 10.4 plus J31.3 ohm when referred to the high voltage side. Again, that's, I mean, Z, you can, that's, I mean, you know, Z1 or Z equivalent 1 is given equal to 10.4 plus J 31.3 ohm. Okay. So that's what else? Taking the transformer rating as base. Oh, was mentioned. Taking the rated value as base. So that's what I did. Determine the base values of voltage, current, and impedance of both sides, high and low. Okay, that's before. I mean, even without saying that, I got to do it. I got to do that. So what I will do that. I will just sketch the transformer here, and that's side 1 and that's side 2. The power is the same, I agree, and the power is equal 10 kVA. So I'll say SB equal 10 kVA, and the same will be on this side, 10 kVA. Okay, then the voltage, I already got it. VB1 is equal, so the voltage base on this side will be equal to 2200 voltage, and on this side will be equal to 120 voltage. Now I want to derive the current base, the impedance base. So I will say IB1, what to be equal to? It's single phase. I divide the power by the voltage. So I'll divide SB by VB1. When you divide it, hopefully I did it. I got 4.55. And on the other side, just make a line here so I don't cross this. Okay. IB2 will be equal the same power, V amp divided by the voltage base 2, divided 10 kVA by 220, you got 45.58. Observe the base values will be like related to the turns ratio. Like, look at the voltage here. That's 1/10. Look at the current. That's 10 times the IB1. It's everything is fine. Now, the last base, the impedance. Remember how we find the impedance base. ZB1 will be, we said voltage squared divided by power. So it'll be VB1 squared divided by SE. VB1 is 2200, you squared divided by 10,000, you get 484 ohm. And find the base for the impedance on the secondary side, you divide it. And I expect it's going to be smaller value. So because the voltage is small, so when you square 220 divided by the same base, then you get 484 ohm. Amazing. The ratio between ZB2 and ZB1, it's A squared. the square of the turns ratio. Exactly when we do the referring from one side to another, it's still there. So we did the first part, and actually, if I was not asked to do that, I got to do it. If you do it right, what's coming is nothing. It's just you are doing nothing new. Let's see. Express the exciting current in per unit for both high voltage and low voltage side. You want the exciting current in per unit. One time on the primary side, one time on the second side. Okay. First of all, the exciting current is 0.25 amp on which side? On side one. Let's just first find the values on the second side in N, and then I will start to work in per unit. So I'll write the exciting current on, it was given, I didn't do anything, and if I want to find on the secondary side, I have to use the turns ratio. I know I don't have strong memory, so I always said, okay, A is equal VB1 over VB2, IB2 over IB1. So I want to change one. So this is I'm getting, which is the IB2 is like IB1 dash. So I multiply IB1 by A. Okay, so the A times I. All right. The turns ratio, we don't have the turns. No, we have the turns ratio. Turns ratio is equal this voltage over this voltage. So we can say A is equal VB1 2200 divided by 220. That's equal 10. So it's equal 10. So I find want to be equal 10 times 0.25. It's equal to 2.5 amp. So that's the value of the exciting current on the secondary winding, and that's the value of the exciting current on the primary side. Now I want to find the per unit. Easy. I just divide the value, the actual value I have in amps, by, I divide by the base value. But I have to remember every side has its own base. So I will write I, phi 1, and per unit value is equal I phi 1 divided by the base in 1. Well, I have 0.25 amp, and the base IB1 is equal 4.55. 4.55 amp. And what you'll get, we need to get it here. The 0.25 divided by 4.55 is equal to 0.055 per unit. Does not have unit, per unit. If you wish, you can multiply by 100, say 5.5%, but this is the way that you deal with it. Even in power system, do you write the parameters in per unit? Some device you real per unit. It's easy. Now let's, yes.
Might be a stupid question, but I one dash, that's just I 2, right?
Yeah. Okay. I'll tell you why I don't write 2. Because I referred quantity from side 1 to side 2. It was not actually 2, but it is 2. Yeah. I agree with you. But why I didn't write it 2? I'd like to distinguish between something originally was there and something was on the other side and got it inside. Because we'll face in some problems like we have already, let's say you have impedance called Z2 and you have impedance equals Z1. Then you want to find the total impedance. What will do? You say equals Z2 plus Z1 dash. Right. Yeah. Now let's find the exciting current on the other side. I write it 2 here. Okay, so I mean, I'll write it 2. Right.
I was just asking.
Yeah, I know. Okay, so now on the other side, which is 1 dash, I will divide it by the base of 2. The value is equal to 0.5 amp, and then divided by the base, current base in 2 is equal to 45.5. 45.5. And the answer would be, what do you observe? Do you observe anything? the same. Yeah, exactly. Is the beauty of period. It doesn't matter. Doesn't matter which side you're working, it's the same value, current or voltage or impedance. Okay. That was the one requirement. The second requirement, obtain the equivalent circuit in per unit form. They want the equivalent circuit. Equivalent circuit means the impedance. It's given, the equivalent impedance was given 10.4 J31.3. That was given on side one, primary side. So what we want to find, the equivalent impedance on the other side, and then I want to find the per unit. But let's first do it step by step. You have the equivalent impedance on side one. Can you get the per unit? Let me write the value here. That's the equivalent impedance given. Equivalent, and the transformer that we have in our hand, that's it was 10 kVA, and the voltage 2200 voltage and 220 voltage, and it's required to find two things. We want to find Z equivalent 2, and then want to find Z equivalent 1 per unit and Z equivalent 2 per unit. Let's start with the first one, Z equivalent 1, what's given, and instead of ohm, want to do it per unit. Okay, so that's what we're going to do. So go ahead and solve this as a question. That's a simple question. Find Z equivalent in per unit. Okay, only 2 minutes. Just one equation.
So sorry, class.
Yes. Yes. Just to get over it, you know. Okay. All right, let's solve the quiz. We need more tips. Now, I mean, we have the equivalent given and want to find the per unit value. So we divide it by the base value. So I'll say that the equivalent 1 per unit is equal to the equivalent 1 divided by the base 1. Because we got two base. I have to choose the right base. It will be 10.4 plus J 31.3 ohm divided by the base value, which we got it here, 484 ohm. 484 ohm. So we get the result. That will be equal to 0.0215 plus J 0.0647. Not of space. 0.0215 plus J 0.0647. And always in per unit, you have to be careful. You write many decimals. Don't round it to 1 or 2, be at least 3. And if you want to find the Z equivalent 2 per unit, first you have to find Z equivalent 2. How you find Z equivalent 2 will be equal to Z equivalent 1 equivalent multiplied by N2 over N1 squared. All right. So we write actually this one, Z equivalent 1 dash. All right. So that will be equal to the equivalent 1, which is equal 10.4 plus J 31.3. And that will be like divided by A square. If you look at the N2 over N1, this is the opposite of A. So actually it's equal Z equivalent 1 divided by A square. And I will divide it by A square. And A is equal 10. So 10 square will get small value. And it will be equal to 0.104 plus J 0.313 ohm. Now we have Z equivalent 1 dash, which is equivalent to Z equivalent 2. To find Z equivalent 1 dash per unit, that's on the second side. So I'll say Z equivalent 1 dash divided by Z base 2. And you divide 0.104 plus J 0.313 divided the base for the second side, it's equal to 4.84 ohm. So we divided by 0.84 ohm, and what we get 0.0125 plus J 0.0647 per unit, which is the same value again, the equivalent one per unit. So once you do it in one side, you don't have to make another calculation for the other side. So the equivalent circuit of the transformer, it's just impedance like that. And it doesn't matter which side actually. That's V2 per unit, and that's V1 per unit. We don't write now V2 dash, V1, no, because it doesn't matter which you are in what side. You solve them per unit, and then if you want to find it in primary side, multiply it by the base of primary. If you want to find the secondary side, multiply it by the base of the secondary. That's it. So that's, I mean, the beauty of per unit. And the impedance is just one. It doesn't matter. Both are on the same side, the same value. 0.0125 plus J 0.0647. So that's the equivalent circuit for the transformer. Let's go ahead and see the second or the third. Find full load copper loss, full load copper loss in per unit. So first, what's copper loss? Copper loss. What does it mean, copper loss? Just don't give me a question, give me the meaning. When I say some device has copper loss, what does it mean? You are an electrical engineer.
The eddy current.
Eddy current. The loss, the power loss should be what, right? Power loss, something lost. And copper, it's like has a historical background, but any power loss in any resistance of any wire, they call it copper loss, because the wire is made of copper, it has a resistance. So before they used to say to call it copper loss. Until now, they still call it copper loss. What it means, I square R. It's the loss in any resistance of the wire. So, and that's what you get in the transformer using short circuit test. That's what you get. So P, and we write it Cu. The copper loss is equal to I square R, equivalent of the transformer. See, I mean, before we used to do the following. If you are on what side, it depends on which side you are. If you are on side 1, so BI 1 square R equivalent 1. If you are on side 2, BI 2 square R equivalent 2. Let's just write that. And now the question said that full load copper loss. R equivalent 1 is given? Yes. Because if you go for Z equivalent, that's Z equivalent. Z equivalent equal 10.4 plus J 31.3. It means R equivalent 1 is equal to 10.4 ohm, and X equivalent 1 is equal 31.3 ohm. So I already know the equivalent resistance on the primary side, 10.4. So I will say that's equal to 10.4. Well, what about the current? Was not given, but it was mentioned that, or they ask you to find full load copper loss. What does it mean full load copper loss? Means that the current is full load. How can you find the full load current of any transformer? You remember we did that in the lecture before the last lecture, Monday. We said that the full load, the rated value, you have the power rated value in volt amp, and you have the rated value for the voltage. So if you divide both, to give you the full load or the rated value for the current. So this transformer was given that it was given that it's 10 kVA. 10 kVA means the rated value at the same time it's the full load. It's also called full load. So the full load is 10 kVA, and you are on side 1 220. So if you divide both, you get the full load current, which would choose it our base, by the way. When you look at it, that's the full load equal 10 kVA, and the voltage 2200, and the current base is equal 4.55. That's the base, that's the rated value, that's the full. So it's by accident, it's the same base. So 4.55. So it's equal 4.55. And then you calculate, you got the couple loss would be 215 watts. The question is, express the copper loss in per unit. So what you'll do? What is the base you're going to choose? Are you going to choose the base for the voltage, for the current, for the impedance, for the power? For the power. Yes. So let me write that as full load per unit is equal to the copper loss full load actual value divided by S base. If I ask you, is base 1 or 2? What will you answer? 1. There's nothing called 1 and 2. It's all only one value. Yes. So that will be equal to 215 watts, and it's 10 kVA, 10,000. The answer will be in per unit, 0.0215 per unit. We don't have amp, voltage, power, watt. It's everything per unit. Beautiful. Well, did you get it? All right. Now let's go for the other thing. Determine the per unit voltage regulation using per unit equivalent circuit. You want the regulation of the voltage in per unit using the equivalent circuit we just got here. That's the equivalent circuit. Well, I will connect. I will say that's Z equivalent per unit, because I don't have something called 1 and 2. But the full load, we need to find the current. And that was given that here the current 75%, because I mean these two are connected. Because I mean when transformer delivers, I mean it's not F actually. This is a complete. When the transformer delivers 75% to full load at 0.6 power factor, that will help you to get the current. So let's just see here the load. That's the load, and that's the source. So that's the voltage of the load. First, it's 75% of the full load. So what do you expect the current in per unit? I want you, without calculation, this is the current of the load, 75% of the full load. I want to express the load current in per unit. Give me value. Yes. And tell me why. I want the load current in per unit. The information given, it's equal 75% of the full load. Right. 0.75. Because the full load will be the same as rated value here. So B1. If it's full load, so current will be equal 1 per unit. Why? Because I mean we choose the current base. On either side, it's based on the full load voltage, and full load power. So if you are using 100%, you divide the same, it will be 4.55 amp. That's the full load current. You divide by 4.55, you get 1 per unit. So when you have full load and you are using the base value related or full load, so it be 1 per unit, it's 100% full load. If 75%, 0.75. Do you see, I mean, how simple now it is, things when you are dealing with per unit? So the IL per unit will be equal 0.75. But you have to be cautious. You don't say, okay, when I see any problem, when you tell me 75% for load, I'll put 0.75. No, don't do that. Check your base. Are you using the base, the rated value, or not? If you're choosing different value, you got to choose. You got to calculate. But in here, it's just because I base equal I rated value. So I full load is equal 1 per unit. Why equal 1 per unit? Let me just make it, because when you divide it, if you want to find I full load per unit, will be I full load over I base. And I full load will be the rated value, and the base is rated value. So is equal 1 per unit. That's why it's 1 per unit when it's full load, because the base is equal to rated value. Well, yes.
Wouldn't you ever take your base value as your rated value?
It's always like that, but some situation they will not take it if it's part of a system and the system has generator. Let's say that generator, transformer, load. You got to have only one base for the whole system. So maybe you are working the load and you're taking generator as a base. So it will not be the same. So there are situations, but if just in this situation, I mean, we have transformer, we got the rate values, we use it, and that's it. So now, I mean, that's the magnitude, 0.7 per unit. Current has magnitude and phase. It was mentioned that the power factor is equal to 0.6, I think. 0.6, yes. Lagging. Yes, 0.6. So we got to find the angle. Because it's lagging, so we got the voltage of the load here. I make it an angle 0. That's the current, and that's theta. So theta is equal cosine minus 1.6, which is equal to negative 53.13 degree. So the current now of the as a vector or as a phasor for the load is equal to 0.75 on angle negative 53.13 degree per unit. So let me just write the value here, 0.75, and the angle negative 53.15 degree per unit. Great. What is the voltage? Nothing mentioned about the voltage. When nothing mentioned, it means working at the rated value. So what is the VL in per unit? One per unit. But they are working at the same value, the rated value. Okay, good. Now we start to get, I mean, it's simple. Per unit make life simple. That's the equivalent given, 0.0125 plus J 0.0647. And now I want to find V1. How you find V1? You say equal VL plus IL times the equivalent plus the drop. V1 will be equal to, as a phasor, equal V2 phasor plus IL times the equivalent. All per unit. I don't have to write. That's right. So let's write the equation here. V1 equal V2 plus I, or call it the load, times the equivalent. All per unit. All per unit. Per unit. Per unit. So VL is equal 1 per unit in angle 0. The current 0.75 on angle negative 53.13. The impedance was equal to 0.0215 plus J 0.0647. That's the equivalent impedance for the whole thing. Well, you multiply the I equivalent with the equivalent and add it to V1 and 0. So we got 1.0486 on angle 9 degree per unit. That's V1 per unit. How you find the voltage regulation? You subtract V1 minus V2 over V2 times 100. I don't have here dash or anything like that. It's per unit. So V1 is equal 1.048. I take the magnitude. Minus 1 over 1 times 100. It will be equal to 0.0486 If I didn't multiply by 100, you get this one. Let me just, if you just write voltage regulation without percentage, that's what you get. You want a percentage, multiply by 100. 4.86%. Even calculating voltage regulation, efficiencies, all the things in per units is really easy, very simple. Because I use the dashes, I'm preferring just any sign, doesn't matter. So that was the voltage regulation. Any question? No question. So I think you have Monday like quiz in the transformer, all right? And I'll put some exercise to practice. And I'll upload the PDF of the 6 now, so we can.